so it's a pleasure to have Matias Zaldarriaga for today's GGI Tea Breaks. Matias is a very famous cosmologist. He needs next to no introduction, but for those of you who don't know him well, he started his career by inventing the mathematical formalism by which we describe the cosmic microwave background perturbations. Today, he was the author of CMB Fast, the first efficient code to calculate the perturbation in the CMB. And then he went on to give many contributions to basically all areas of cosmology, from inflation to large-scale structure to recently the physics and the data analysis of the gravitational wave signals. And this is the subject that he will talk about today. So it's a pleasure to have Matias, and I give the microphone to you. Can you share screen, Matias, please?
Yeah, great. Thanks very much for the invitation. So as Guido said, I am used to be a cosmologist, maybe we can say, but at least this part, this talk is not very cosmological, and so this will describe what we have been doing in the last few years with various people at the IAS. So so this is the group of people I've been working with in this area. So the people on the top row were the ones that, and myself were the ones that were involved in reanalyzing the LIGO data from the previous observing runs. I'll describe that a little bit. Javier and Seth are students, the rest are postdocs. Horngsheng has just joined the IAS. So so we spent quite a bit of time reanalyzing the LIGO data. We found some other events that they had not found. I'll discuss this a little bit, but of course, since we did that work, LIGO put out a catalog of new events from their third observing run, which had many more, it was a more sensitive time for LIGO, and so they had many more events. So a lot of the astrophysical interpretation and questions are now driven by the vast number of new events that they put out. So that is a piece of data that we have not been able to reanalyze because it's not yet public. It will be in shortly. I don't know if there will be some delays or something, but otherwise it will be in the next couple of months. And so I cannot tell you what we can say about those data. They have put out little pieces of data about around the individual events that they report, but not the entire data sets, so that people can look for other events or assess the significance of the events that they put out, because they just give little chunks around each of them. So whenever I tell you about like what we have learned about the properties of the sources and so on from the new events, I will tell you about our data, our parameter estimation based on the data they put out and so on. It's our take on it, but it's not so different in many ways than what LIGO has done, because we don't have access to data to do much better than that, but or much different than that. So anyway, so the plan of the talk, I'll give you just some brief introduction to make sure that we're all on the same page about the gravitational waves, and point out a few things to remember. Then I'll spend, I think, most of the time talking about the current status of the observations with all of these new events, and highlighting for you what I think are some of the interesting puzzles that this data is telling us. They're mostly probably about the astrophysics of the formation of these black holes and the black hole binaries. There might be some room from, given that there are certain things we don't understand, I suppose there's always room for some new physics or some new phenomena that we don't quite understand, perhaps not of astrophysical origin, I don't know. And then I'll tell you a little bit about what we had done with the previous data, just to highlight the work that we had done before. But in terms of the number of events, in many ways, the things that we found, although we found some curious things, so like potentially lensed event, things like that. But other than that, for the bulk of the numbers, they are now dominated by this new release of this data of the observing run 3. Okay, so just the very fast introduction. Gravitational waves, as you know, they come in many frequencies. They tell us about different things in each of the frequency ranges. And today I will be talking mainly about gravitational waves that can be observed with ground-based interferometers, frequencies around 100 Hertz. Just to remember that. And the sources of those gravitational waves are mergers of neutron stars or black holes, at least so far. Perhaps, you know, other things will be discovered, but I'll be talking about neutron stars and black hole mergers. Just again to have everybody on the same page, most of these or all these events are coming from the mergers of some 2 black holes, for the most part, a binary neutron star in observing run 2. When these compact objects are very near each other, they start their main reason they start losing energy is the emission of gravitational radiation. So as time goes by, the distance between the 2 compact objects decreases, the period becomes shorter, energy, the power being emitted becomes larger and larger, and so you expect, in terms of the gravitational wave, this chirping of type signal, in which it starts at low frequencies when the objects are further away, and it starts going faster and faster and faster as they lose energy and eventually merge into a single, say, black hole. For the most part, LIGO is in some sense the final stages of this. Everything is moving quite fast and quite relativistic during most of the, especially with the binary black holes, it's just we see them at the final few, depends on the mass, the final few cycles. Just again, just to have to have another picture in mind. So again, the same kind of thing. So I will be talking about, when I discuss this or people, and in the talk I will be the binary system. Usually people characterize by either the total mass or the mass ratio Q, which is the ratio of the 2 masses. There's something else called eta, the symmetric mass ratio. There's something else called the chirp mass, which is some combination of the mass and this mass ratio. And that's what dominates the time evolution of the chirp mass, is what dominates, what sets the leading contribution to the time evolution of the frequency of the gravitational wave. So in the time domain, the frequency scales roughly in this way as a function of time. Sometimes it's useful to discuss the gravitational wave. So there's 2 figures here. One, you can see that the train of gravitational wave as a function of time. If you were to Fourier transform that curve and plot the amplitude, so that the Fourier transform would have an amplitude and a phase. And the amplitude is plotted in the right plot, where you can see that it's kind of a power law, the exponent at lower frequencies, when the thing is what is called the in-spiral phase. It's roughly speaking the frequency to the -7.6. That's the and this you can figure out easily from quadrupole radiation and so on. Then eventually there's a cutoff when there's the merger. So there's a maximum frequency given basically by the size of the horizon of the combined thing. And you can see that there's a little plateauing, more energy is being emitted near the merger, and the size of this plateau a little bit depends on the relative spin. There's many formulas that I can give you. For the most part, for the gravitational waves from binary black holes, they're happening towards the end. So analytical formula, like the PN approximation and so on, they have some limited range of validity. A lot of the signal to noise comes from the very end, where we use people use numerical relativity and interpolations of numerical relativity to build these waveforms. So here are examples of these formulas in the PN approximation for the amplitude and phase of the Fourier transform of the gravitational wave. So in the PN approximation, it's an expansion in powers of V over C, and there's many terms. X here is related to that. I just put these formulas for you to see that if we were in the PN regime, the lowest, the dominant term, the lowest that is most important at low frequencies when they're far away is this first term that only depends on this chirp mass. This M tilde is the chirp mass. As you go higher and higher orders in the PN expansion, more parameters of the binary start being important. The next thing that becomes important is this symmetric mass ratio eta that enters in the next term, although with coefficients that make both because of the way eta depends on the mass ratio, it's symmetrized. So around mass ratio of 1, eta is 1/4, and it's quadratic in the mass ratio. So it's not very sensitive to this Q parameter, this eta. So it's a difficult thing to measure, this eta. And then this beta is to do with the spin orbit, the spin in the direction of the orbit. So, and chi's here are the spins, L is the orbital angular momentum. So some combination of the spins in the direction dotted with the angular momentum. So there is some spin orbit coupling, and in terms of the phase, or maybe some heuristic way to think about it is that when the black holes are spinning and they are spinning aligned with the orbit, eventually when you're nearby, the first thing, there is some sort of repulsive type additional force. You can think of it like this, that delays a little bit the mergers, that changes the phase and makes the thing a little bit last longer, and thus a little bit brighter in the end, that you can see it to a little bit further distance. And then if you go further down in this expansion, you start seeing the components of this enters the sigma, which is has to do with the components of the spin in the direction of the plane of the orbit, as opposed to along the angular momentum, and so on and so forth, more and more parameters. But roughly speaking, at the current time, with the kind of signal to noise that we have for these events, you can determine the mass and or either the chirp mass or the total mass, one overall mass parameter very well. Mass ratio, not so good. The spin in the direction of the angular momentum, pretty good. It depends on the mass and so on. And other things, the spin in the plane of the orbit that causes precession, for example, not so good. So main things that we learn about these individual events so are the mass, especially the chirp mass if the mass is kind of lowish, and the chi effective and the mass ratio. So this chi effective, sorry, is a combination of the spin in the direction of Z here is the direction of the angular momentum. So it's just the spin orbit coupling weighted by the mass of each of the, so you reduce it to a single parameter to, again, telling apart who is the one that is spinning is not so easy of the two black holes, let's say. If the two were spinning aligned with, so if they are spinning not aligned with the angular momentum, difficult to detect. If there's the component of the spin along the angular momentum, is easier to detect, but separating which one is of the two black holes is the one that is spinning, not so easy to detect. So that's just to give you some sense of what one can learn. So these are a little plots of in the y-axis frequency, on the x-axis time, and the color on the background looks like the amount of power that you're seeing, so that you see that frequency is going up in these events as time progresses. So this chirping phenomena. But what I want you to get from this figure is that the amount of cycles, so what's plotted in the bottom is basically the waveform that best fits the data over the frequent over the range of times that where the signal was being emitted in the frequency range that LIGO can see. And so you can see that the number of cycles being plotted in the different for the different events is quite different. The binary neutron stars, you know, a huge number of cycles in the band. But for these more heavy black holes that merge at the maximum frequency is lower. Again, this is given basically by the size of the horizon of the merged object. So the frequency is lower, the maximum frequency is lower, so there's a smaller number of cycles that it spends in the band. So the range of times to keep in mind is a small fraction of a second, point something seconds for the shorter one. The binary neutron star takes forever. But so of course, then the heavier guys for which you see less cycles, then your ability to fit parameters, or it becomes less good than the things that are a little bit lighter and they spend more time in the band and they have many cycles and so on. So the error bars of parameter estimation very much are correlated with the overall mass of the event. Okay, so that's some very fast review. We can learn from these observations about properties of the black holes and the neutron stars, perhaps something about the loss of gravity when in this regime, perhaps if there's any doubt about GR, and then the processes that resulted in these black holes and the black hole binaries, and that's what I will mainly be talking about. So what is the status of the observation? As I was saying before, LIGO, this set of observations for LIGO are what it's called advanced LIGO. There was an observing 1.1, an observing 1.2, and an observing 1.3. On the right here on the bottom, you can see the cumulative number of events observed that they reported in 01, 02, and 03. So you can see the big increase in the number of events in 03 as the detector becomes more and more sensitive and it's able to see objects up to a larger and larger distance, okay? So the highlights on 01 was just the discovery. Everybody was very happy. In 02, they saw the binary neutron star. That was perhaps the highlight, and that allowed people to, you know, confirm that the gravitational wave speed is the same as that of light to, I don't know, some ridiculous number of decimal places, and then have quite a bit of fun trying to model both the, you know, the explosion, that the so-called kilonova that came after, and what kind of material was ejected, what was it made of, and etc. Now, in the observing run 3, what has changed is just the vast number of events that they have reported, and so here is a picture from one of their plots where you can see for all of the events. So just to get a sense of, so these gravitational wave events are labeled GW and some date. Everybody that's 19 somebody, so this means 2019, that's observing run, an observe event from observing run 3. Anybody whose name is GW17 something, that's observing run 2. Anybody that has a name GW15 something, that's observing one run from 2015, 17, and 19. But so there's a vast number now of 2019 events. And this little plot on the right shows you kind of for each of these events some of these parameters. So the masses of the two components of the black holes, M1 and M2, their mass ratio, and this kind of plot, I don't know why they like it, but it's some sort of it shows the posterior of this parameter. The top, you know, it's like a little violin, they call it. I don't know why, anyway, but it's just the width of it is to do with the top. It's symmetric top and bottom, so the width gives you where the probability is, and so you can see there are measurements of the masses, there are measurements of the mass ratios, there are measurements of this spin parameter, their distance, and so on. So many events, and so now the goal is to do some sort of try to understand the origin, the formation of these black holes and black hole binaries based on this increasing number of events. So let's discuss this a little bit now. So the first thing to discuss is the masses of the black holes. And I think from the very beginning, I mean, what most of you, I'm sure, heard was the LIGO black holes are very heavy, okay? And the main point is if you look at the black holes that we had detected in binary systems in the Milky Way and nearby, when the black holes accrete matter from some companion and emit X-rays, they're so-called X-ray binaries. Those black holes had masses, you know, the heaviest one was around 15, Cygnus X1, for example, was around that mass. And all of the LIGO black holes from the beginning were kind of heavier than that. Now there are some that are, I mean, it's more interesting, but for the most part, they were heavier than that. So you can see this in the plot on the right, where there's just for each black hole. I mean, I'm sure you've seen this plot. It's direct from LIGO. So for each black hole that they have for each binary system, they have 3 black holes there, the 2 individual ones, and then the combined one. There's also shown there some estimates of masses of black holes from these electromagnetic observations. If you want, you can see that those tend to be much lighter than all of the LIGO black holes. And another thing that was kind of interesting is that at least for these black holes in these high mass X-ray binaries in the Milky Way, the people had estimated the spin of the black hole, and it seemed to be very high. I mean, for example, this Cygnus S1 is consistent. At least, I mean, there's some modeling uncertainties and maybe debates, but roughly speaking, it's consistent with maximal spin, while all of these LIGO black holes starting from the beginning didn't seem to be spinning very much. And so that presented some sort of puzzle. I mean, I think it's complicated to try to understand the mass of the final black hole that you produce if you start with a star of a given mass, exactly what mass of the black hole you will end up with. It has many uncertainties. This star, you know, loses, this heavy, very massive star lose a lot of mass in their lifetime. And in order to explain the population of black holes in the Milky Way, people, you know, in their models, everything was tuned so that the maximum mass of the black hole, or that the black holes came out with 10 solar masses, and then suddenly all the LIGO ones were heavier than that. And I think just for completeness, the standard way around this, I mean, these stars lose a lot of mass in the form of winds through their life, and a lot of these winds are produced by the radiation pressure from the star pushing the material in the envelope out. And the idea was that this opacity of the material depends a lot on what it's made of. So if there are a lot of heavy elements, there's a lot of lines, absorption lines that make it easier for the wind to be pushed out. And so one simple workaround that people implemented immediately when they saw this was to claim that the black holes from LIGO were coming from environments with very low metallicity. And so the stars didn't lose mass as much. Whether this is the answer is not clear. And for example, even in the past, in the past week or so, the mass of Cygnus S1 was moved around, even though, and by new observations, and it looks like it's now heavy, like 20 solar masses, and it's pretty metal rich. I think it's or heavy elements, a lot of heavy elements, so much more than the sun. So anyway, this whole picture, I don't know what's the situation. Whether, you know, there's some truth to it, but in detail, I don't know. So the black holes of LIGO are heavy. This is a little bit of a puzzle, but it's a complicated astrophysical puzzle because the connection between the mass of the star and the black hole is complicated, many parameters, and so probably an elephant can be, adjusted. Anything that you see can. But it's an interesting point. If there's any questions, feel free to stop me, because if you expect me to look at the little hand in the Zoom, it's not going to work, because I don't know. It's too complicated for me. So, but I'm happy somebody.
Okay, so this is Aman from India. So my question is that
somebody stops me like at random.
Yeah. So in the last image, you said like so there is something called this black hole mass gap. So
yes, I was going to go about it in the next slide.
Okay. Fine. Okay, fine. Go ahead.
Okay, so this is a.
Sorry.
Okay, sorry. So let me again. So this figure, x-axis 0 H-man sequence mass, y-axis is the mass of the compact object left over. Okay, and you can see in terms of this mass of the compact object, there's these gray regions where there is no compact. Follow one of these solid lines. The different colors depends on the metallicity of the star, but you can see that the black holes that are resulting are so. The below 2 solar masses for the compact object, that's a neutron star. Then suddenly, when the mass of the star, the original star, becomes heavier, then eventually you start producing the black hole. And so there's the supernova explosion that produces the neutron star, instead of, all of the mass goes out, or a lot of mass comes out in the supernova explosion. If that doesn't happen, you end up with some black hole whose mass is larger than that of a neutron star, perhaps 7 or 8 solar masses. I mean, this is a little bit. So the idea is that there's some sort of gap between the maximum mass of a neutron star and the minimum mass of a black hole. That's so-called the low mass gap. And then eventually, if you go look past 40, 50 solar masses, you also see that even you also don't have any compact object of this mass. And what happens there is that as the star becomes more massive, eventually in the core of the star is becoming hotter and denser, and eventually it's hot enough. There's supported by radiation pressure, and this radiation is energetic enough that can produce pairs, electron-positron pairs. And so then when you reach this threshold, a lot of stuff start happening. You're losing a lot of energy into producing these pairs. This leads to various pulsation type instabilities of the star, and eventually even some explosion that blows up the whole thing. And so the idea, and this seems to be pretty robust, that once you pass this mass for the core, you blow the thing up and you don't have a compact object left there. So there were these 2 mass gaps. Eventually, if it's too much heavier, then this explosion cannot take anything out, and so everything falls in, and you have a very heavy black hole. But there were supposed to be these 2 mass gaps, and in O2, the data of the different black holes and the neutron star binaries and so on is plotted in the most left of the plots, and everything seemed kind of consistent with this picture. This stopped to be so with the new events. And I think it stopped to be so if you believe the events that we had seen, which I believe. So now this is what I'm doing here is just I'm taking the heavier of the events that are there, and I am plotting their constraint on the mass for each of the events. The vertical line on the left in the plot is this 40-50 solar mass cutoff of this due to this pair instability supernovae or pulsation instability. That's which is, as I was saying, pretty robust. People, if you try to see how much this mass cut changes with the metallicity of the star, or various things that you can do, various uncertainties in cross sections, and so it's not very much. So it doesn't move very much. So, but now you can see there are many events that seem clearly to be heavier than that. So I plotted all of the heavier ones that we have, and there's a lot of them, and there's the names of those events that I plotted there, and you can see, okay, there's a bunch of 19 something or 19 whatever events. Those are all the 03 events. There's a bunch of 17 something. Those 17, which are 4 of them in this plot, those in some sense, except for 170729, these were all events that we found that LIGO did not in the LIGO data. So if you looked at this, and even 170729, it was an example of something that LIGO claimed was like barely significant, but for us it was super significant. So so I think already at the time of the end of the O2, if you look at our results, you would already have seen that there were several things that look heavier than that. So let me spend a little bit of time now talking about the difference between our pipeline and the LIGO pipeline, just in terms of results, and in terms of the different things that we are doing. I will discuss that at the end if I have time. So, as I said, I think it's a very nice example to look at this 170729 event, which was there in O2. It's an event reported by LIGO, but its significance very much depends on how you're doing the analysis. So the parameters of the event, no, once you're giving the little chunk of data around it, you fit the parameters, everybody will more or less agree on the results of that. But how significant that is, that event was, will depend on who's doing the analysis. And the reason for this is that what we are doing in the search is to take the entire LIGO data. We have a bank of shapes of waveforms that we're looking for. We search for this waveform in all of this data, and we have to assess what are the chances that when we see some piece of the data that looks to have an event, what is the chances that this is an actual event, and not just because we are searching for so many templates in all of this data and so on. And so the important really, so the significance is something that you can assess only when you have all the data. And in particular, the important issue is that this data is not an ideal Gaussian random field of data. It has a lot of artifacts, and it's how you deal with those artifacts that can lead to vastly different significance for the same event. Because if the data has a lot of artifacts, but you manage to flag them on the basis of something else and cut the data in the places where it's not behaving very well, then the same event, and this particular event that you're discussing, it doesn't fall in these bad pieces of data. If you manage to clean the data so much that it looks like a Gaussian random field, then you would get one answer, and if you didn't manage to take out all of this imperfection as well, you will get some other answer as to how likely this particular event might be to have been produced just by noise. So this is an example. Let me see if I can explain this plot. So when LIGO reported 170729, it said that its false alarm rate, the chances that this thing could have been produced by noise in their detector, was 1 every 5 years. So it was a decent thing, but it was not. I mean, the run was let's call it a year long, and less than that, but a little bit less than that. So chances, it was not impossible for noise to produce it. For us, when we did this estimate, the chances that that event, we could not even assess it. We produce a background of 20, equivalent of 20,000, which is like 6,000 years or something worth of data, and we wouldn't see anything similar like that even in all of these backgrounds. So what is plotted on this plot? So there's two axes, and what's being plotted in those axes is the value of the, when you are searching for a particular template, the overlap of the template with the data at the value of the event. If the just to get a sense, if the data was just a Gaussian random field of noise, then the probability distribution of this rho square would be basically e to the minus rho square over 2, just the Gaussian. So this is just the number of sigmas in the Gaussian. There's two axes. If it were a Gaussian, there's the two axes. One is called H for Hanford, the other one is L for Livingstone. So anybody that has a very high value of these, naively, if everything was a Gaussian random field, then it would never be produced, right? Because the chances would be down by e to the minus 120 over 2. So for example, in the ends of these. Of course, we have searching for many templates many times and so on, but that after the rho square is of order 7 square, like 50 or something, maybe depends on, but 50, 60, then it's the chances of being produced by Gaussian noise is very small. So what is plotted in the dark kind of histogram, those are our background events that are produced in the following way. You just, as you know, there's these two detectors. You should see the gravitational wave on both. There's a little bit of a time delay depending on the direction of the sky, and maximum is like 10 milliseconds. So if you look at two pieces of data that are in Hanford and Livingstone, which are not within 10 milliseconds of one another, but you know, a longer this time lag than that, and you see something that looked like an event, that you see something in both Hanford and Livingstone, you know it's a fake, that it's not a gravitational wave, it's the background. This is the background that you, so a way to estimate the background is to just shift the data many different times and repeat your whole procedure, see if you see something. And those are the results of the black points. And so you can see where our background is distributed, and you can see the position there of 1707.29. There's just nowhere near, no dot ever fell anywhere near there for us. But for LIGO, there would be many of them, because each time they generated 5 years worth of background, they would see something, you know, in that location. So I mean, I will, maybe if I have time, I will talk more about this plot later, but what this plot is just the probability distribution of these of triggers that have a particular rho square, the same as is plotted here in the X and Y axis. So if everything was a Gaussian random field, the distribution of this would be e to the minus rho square over 2, which will be just a line in this plot, more or less like the green line is in some of the plots. But when you see these other distributions that have a tremendous tail, those are these imperfections in the detector, and we worked on two of them. One were little times where there's various what they call glitches. So but they don't look quite like gravitational waves. But if you put a template around there, they will pick up enough power that, and so we try to characterize those and learn how to kill them. And so we throw out a lot of data whenever we see something fishy in some frequency range or something. Kill. So we are happy to throw out a lot of data. So in our search, anything that looks suspicious, and what suspicious means, it takes a lot of time. It took a lot of time to try to figure out. And so a lot of this tail is reduced when we use these vetoes. And then the other thing that happens, and I will discuss perhaps later if I have time, is that the noise in this detector and all the properties of the detector change with time slowly compared with the tens of milliseconds of a gravitational waves, but in a time scale of I don't know, few seconds or something, the error, the amount of noise in the detector is changing. And if you don't, but you really need to track this very fast in this 10 of seconds of time scale, because if you don't do so, what happens is that whenever you have a misestimation of the noise of 10%, let's say, which happens all the time, then it's much easier for having such a high sigma event. These are, you know, sigma. 10 sigma thing. These triggers are 7 sigma things, 8 sigma things. It's much better to wait for the time in which you have a 10% error in the noise. So you think that a 7 sigma thing, an 8 sigma, something that is 7 sigma, you assign it an 8 sigma. To get an 8 sigma thing like that is much more probable than actually waiting for 8 in the Gaussian. So if you have the wrong variance, you start generating a lot of high signal, what appears to be high signal to noise trigger, just because you have 10% mistake in the variance. So that was another source of, but this just to say that depending on how you treat the data, the background that you end up having for these searches is very different. So the significance that you might assign to some of these events is very different. And so that's the reason we could find some more events. And the case of 170729, for us, it was super significant. And so already, if we go back here, already at the end of 02, you can say there were several events that looked heavy compared to the cutoff. Okay, good. So there's something going on there, something about this pair instability thing, or perhaps these are some second generation. So perhaps these are these very heavy black holes are ones that were formed in some other way. In fact, if you start trying to model the distribution, what you discover is that there is some sort of feature around 40, 50. You cannot extrapolate. The distribution of events as a function of mass is more or less well fit by a power law, but by the time you get to 40, that's not a very good fit. You need to do something. The number of events that you're seeing is not so high. It's clearly, there's a decrease of events heavier than around 40, 50 solar masses for the primary, but it's not that they cannot be produced. There's some there. So that's an interesting situation. In terms of the this low mass gap story, again, there were in the 02 event, 03 catalog, there are 2 events that one that who's have a companion that is below this cut. Of course, this could be a neutron star black hole example, and there's one of them, 190426, which people think might be a neutron star black hole event. That's again in the way LIGO. For LIGO, this is a very borderline event. Its significance is not very high. We'll see if when we get a hold on the data and we try to analyze ourselves, maybe it becomes more significant for us or less or something. I don't know. Very interesting to see if that's the case. So that's perhaps an interesting example of a new type of system, or a black hole that is lighter than what we think, or a neutron star black hole. More interesting, perhaps, is 190814, which is very well measured and very high significance and so on. And its mass is heavier than what we think is the heaviest possible neutron star, and is definitely lighter than what this mass gap suggests. So again, another puzzle there, which hopefully with the events that they have already in the can of the second half of 03, maybe there are some more examples of these, or maybe the significance of some of them can be reassessed, or maybe we can find some more. I don't know. It's interesting to see what happens here. I'm plotting also here one of the one events, the Boxing Day event, but let me not discuss that. I'm putting it here because when we do now the parameter estimation with some more recent waveforms with higher modes and so on, we do see a significant amount chance that this guy has one of the black holes is light. So I don't know, but it's contrary to standard lore, but maybe I just skip that. So that's about the masses of the individual black holes, but then there's the question of the black hole binary system. Okay, so how did this come about? And the main issue is that for these binaries to merge through gravitational radiation, they need these two black holes need to be very near each other, much closer than the radius of these stars, especially when they go through their giant phases. So somehow you need to end up with the black holes that are very close compared to the size of the stars. So there are two main channels that people discuss for the formation of the binary system of the two close black holes. One in which you start with a binary star, two binaries, a pair of stars, and they evolve in the giant phase and so on, and one of them becomes a black hole. Eventually, the other one becomes large, maybe it engulfs the other black hole inside of the envelope. This produces some sort of friction in some stage called the common envelope phase, in which the black hole spirals in towards the core of the other star. That energy is used to eject the envelope of the second star, and that's how you end up with the core of one star and a black hole, and then eventually the core of the second star explodes and forms the second black hole. That would be the classical channel of formation of the black holes in a binary system. And another one option is to form the black holes separate individually in some high density environment where they can find each other and get captured, and their orbits through three-body interactions with the other in this dense system with a lot of stars starts finding each other and forming binaries and tightening these binaries until eventually they're close enough to emit gravitational radiation. That's usually called the dynamics kind of channel. So there are places like globular cluster that have many stars, are very dense. This could happen there. In terms of the physics of the formation of these binaries, it's much more fun to play around with these n-body codes and so on. It's much cleaner situation than this binary evolution with the common envelope, which is all like cooking what's going to happen. But so these are the two channels people are trying. Everybody's trying to see. I mean, and these dense systems, there's variations of these. These dense systems might be also the central regions of around the supermassive black holes in the center of the galaxy. There are other options, but one hope is that to see if from the distribution of the parameters of these events, you can distinguish between these options. And a good way that perhaps a clean test is to look at the spin orbit, which is something we can measure now, and it has a clear signature of this because of the following. If you form the two black holes separately and then they come together, their orientation between the spin of the black holes and the spin of the binary they end up is completely random. However, in the other case in which the two stars form together, the spin of the stars in many situations is very much affected by the tidal force of the other star or the black hole near the companion core before the final, when the object is much larger, so it's easier to spin it up, and there's the perturbation from the tides of the other guy. So you end up preferring a spin that it's related to the orbit. So any preference that you can see of the spin with the orbit is pointing to these two things forming together in some and being in that orbit when they were larger and tides could affect them than when they were black holes and basically their spin is set. You cannot touch them, like in the dynamical case. So okay, so this, let me skip this. So what is the situation with the spin measurements now? So let me plot this is a plot of this parameter chi effective. Again, the spin in the direction of the orbit. So a positive value for this chi effective means that the spin of the black hole is preferentially aligned with the orbital angular momentum. A negative value means anti-aligned. It's a weighted sum of the spins in the z direction, which is the orbital angular momentum of the two black holes, just to reduce it to one number. Any preference for positive versus negative may be a good sign that at least at some level this binary evolution channel is playing a role. And so what I'm plotting here on the left is just for each of the events, there is a measurement of this chi effective, and I've divided the chi effective by the width of the posterior of the measurement error. Okay, so if everybody was not spinning, you would expect a distribution for these events that is a Gaussian of unit variance around 0 for this chi effective. If nobody was spinning, that's what you would expect. And so I'm plotting here the cumulative distribution. So for each guy, I'm putting 1 point, one after the other, of these values of chi effective started. And what you can see is the following. First, the lines is just a cumulative. Let's look at the highest one. It would be the cumulative distribution for the 30 events that I'm having in this plot of a Gaussian of unit variance. Okay, so if nobody spin, the distribution, the cumulative distribution will look like that top line that says n equals 30. Clearly, it's not what these points look like. With 30 events, you don't expect anybody above 2 sigma, right? If it is a Gaussian distribution. So anybody that you see here above 2 sigma is suspicious. It's spinning too much. It's not consistent with 0 plus noise. Okay. So first, that you can see there are several events with detected spin that is not consistent with just being 0, even after the fact that you had many events or 30 or whatever, and they are all on the positive spin side. Okay. So okay. So, and if you try to fit the distribution with you know, the best so this dark line is, let's say there's of these 30 around, it looks like you can fit around 20 with a distribution with something that are not spinning, but after that they're just you just cannot do it. So you can imagine that there is 2 populations or something, one we are not spinning, and then other ones that are positively spinning. I mean, you need to, it seems that you need to add something with positive spin. So this, to me, is pointing to the standard channel playing some role here. On the right plot, you can see the left. I just did the chi divided by the error in the chi effective divided by the error. On the right plot, I'm just plotting just chi effective, just the spin. So, and this just shows you that a lot of these events, like the ones that you see here, for example, they have well measured spin, different from 0, but still small, right? So, for example, most of these events, their mass ratio is consistent with unity. So if one of the black holes was maximally spinning, you would get a value for this chi effective, which is around 0.5. So most of these events that are very significantly spinning are not 0.5. They're significantly smaller than this. So it's not that one of the black holes is maximally spinning, which is something you might, in this story with the tides, let me not get into that because I'm running out of time, but you might expect that maybe the simplest minded toy model is that when the black hole is close enough to this, when you before you had the two black holes, you had a black hole and a star. The tide from the black hole would spin up the star that did not quite explode, the core of the second star. And it's very easy to, when they become tidally locked, that the amount of angular momentum is much higher than what is needed to have a black hole of spin of 1. So you might expect that perhaps the second guy to explode ends up in some situations to have a maximal spin, but it's not, does not seem to be the answer here. And this is try to do the similar. So I think the conclusion from this, and the next slide I'm going to skip, which was a more quantitative way of doing it. This one is just just so you can see it with your eye. There seems to be some preference for positive spin. They're not spinning fast, the black holes, that, but they're significantly spinning. So it's a little bit of a puzzle what's going on. And so I think I ran out of time already. So let me not discuss very much our search. Just to say, the summary is that we found one new event in the 01, 6 new events in 02. Some intriguing lensing examples. So we found a lot of things, some with less significance than others, but we believe that it's not that we changed the criteria by which something is declared to be an event, but we think our search was more sensitive, roughly a factor of 2 in volume. And that's the reason why we were able to do this. And we hope that LIGO data it becomes public soon enough, and we will see if we can do this again on 03, although some of the simplest things that we did, they were already incorporated by the LIGO pipeline. So perhaps the upside is smaller than it used to be. Okay, so let me finish there because I don't want to bore you too much more.
Hello, Matias. Thanks for a great talk.
How are you? Thanks.
Can you say just a little more about what's the difference sort of between your templates and the LIGO templates that resulted in a different number of events? Also, did you get, I mean, I'm not even sure what's fully public. Is the full stream whenever they're in lock, is that available?
Yes, for 02, that's what is available. 02
Yeah.
and 01, that's what is available. Things that are not available are, which we have, we are now collaborating with them a little bit, is they have also a lot of additional channels to monitor some of these imperfections. That is not available. So it's just the stream of their best estimate of the strain as a function of time whenever the thing is on. Okay, so let's see. So let me just say, what are the, just to be very quick. So what are the steps in one of these pipelines? You have to compute waveforms. You have to then make them into some sort of bank or list of waveforms that you're going to search over. You need to be able to estimate the detector noise and how it's, because and very its non-stationary nature, detect all of these bad segments, glitches, a lot of things. So in the color coding here is something that is green, we are doing the same as LIGO. Something that is red, we are doing different than LIGO and in a different way. And I mean, the pipeline we wrote, so every code is different except for computing the waveforms. The actual waveforms, we get them from the same place. Not made them into a bank, which waveforms to choose, all of this is different. But So there are a lot of differences. The things that are in red is a little slightly different way or significantly different way. Things that are in blue is just, we are doing basically the same thing that they are doing. It's just our own code. Let's see. So, you know, these are examples of these glitches. We are very aggressive in throwing things out. So that's a difference with LIGO. So, you have to be careful when you throw things out, and so that it doesn't pollute the neighboring times, because, okay, maybe I go to say this. One of the issues here is that this noise has these very narrow lines. What this means is that in order to take this, so you have two options. In this narrow line, you're not going to see anything, but you need to filter it out. But it's so narrow that in order to be able to just filter a narrow place of the data, you need a long time span of data to have good frequency resolution. This means that all your filters that you're using tend to be long. And so if you do something locally, you screw up far away as well. And also it's difficult for you to track how things are evolving if they evolve in a 10-second time scale, if you need hundreds or 1,000 seconds in order to resolve these lines. So there's a lot of technical things like this that we are doing quite differently. And I think that's the reason that we end up with a background that is very much different than theirs. And you can see from this plot that all of these events, so if you just take a look at the plot on the top left, so if, when you just mask the things that LIGO in there, they also have some flag that they give you, just bad time, only that, you can see this huge tail. All of this work that we've done, it's many orders of magnitude of trying to, improve things. So you can see how, and if this happens in the two detectors, the probabilities are the product of the, if you have a trigger in Hanford and Livingston, I mean, of course, LIGO does something. All of this improvement is not that their thing has no improvement. So somewhere in between these two lines, the green line, which is our final thing, and the original thing is where LIGO is at. But there's many orders of magnitude there. And this difference gets squared when you have two detectors, right? So it's not a surprise that one can do differently, that the results are not going to be the same. And there might be some regimes in which their thing is slightly better than ours. We had in hindsight, we did this thing already knowing that they had seen heavy black holes. So we spent a lot of time trying to make these banks as clean as possible and this green distribution to look like this ideal e to the minus rho square over 2 or whatever it was. They didn't, I guess, have that in hindsight at the beginning, but they do now. So I don't know if we will be able to do as good in 03.
Thank you.
Okay, Zurab.
Matias, thank you for so nice talk. Hopefully we will find slides and after your talk.
Yeah, I'm happy to.
I wanted to ask immediately several questions. So you have shown the spin distributions in one of the slides. And the last event, which is well above it's 0.75 or something like compatible. It's from your pipeline or from LIGO? And
no, LIGO.
LIGO.
Anybody that has a 19th name is from them, because we.
Okay.
I mean, for this plot, the actual value of the spin for the event, I'm reporting what we get when we feed the parameters, but it's not too different from what LIGO gets.
Okay. These are both companions very heavy, or this is considerably lighter event because it's.
No, this. So that one I think has both heavy, but let me say one more thing that went into the plot. So, if in some previous slide, I show you how many events LIGO had total now, and it's more like 50 events. What I did here for this plot is, that's why it's called gold sample. I was very so any event which is dubious because it was seen by only one detector, or there are many pipelines that looked for it and only one saw it, or its significance was, its false alarm rate was not very low. So the borderline events for this plot here, I removed, so that anybody that is here, you are 100% sure is a true, is a true event. So that's, so these guys are real. It's not a dubious guy. The more lower significance events are not even in this plot. They don't change the conclusion about like the fact that there's a difference between positive and negative spin. In this plot here, I'm showing results. I didn't discuss this, but just to tell you that you can then do the analysis with everybody and just not to try to bias yourself or whatever, but just to see by your own eyes, I think it's better to just put the guys with the smaller error bars and that you're sure that you are believing in them. And this is what is going into this plot.
Okay, there are some events which are even maximally spinning. Just if you could remind what were the companion masses of this most spinning event?
1905-17. I don't remember, but maybe I can go here. 1905-17. So this is not a particularly heavy guy. So these are the two masses, M1 on M2. So they're both below 50. I mean, so something like that. The mass ratio consistent with 1.
But not from light category. And about the event distribution, I had questions which I immediately didn't understand. When you show your distribution of very heavy events, which is this one, these are final masses or initial masses? Which I cannot...
This is the masses. No, this is in the source. This is the mass of the heavier black. No, this is just, sorry. M1 is the mass of the heavier black hole in the rest frame of the event.
Okay, because
so this is just to compare with the supposed maximum mass of 40 something, which is the vertical line there from pair instability supernova. So these are all events which apparently the heavier of the two black holes are above this cut.
And here brown ones are which you found.
No. The color is just a random thing that this matplotlib is giving. The ones that we found are the ones that the line is solid and are the only ones that have a 17 in their name, because we didn't have access to the 19. So
which ones are, if you could point?
So this one are the ones that that are coming from us. And also 170921, which I probably is this one, is the one that I discussed that the LIGO was giving like a false alarm rate of 1 every 5 years, and for us is very short. So this was found by LIGO, but if you were to look at the LIGO papers, the only one that perhaps is a little bit heavier than the cutoff was this one, and maybe you can wiggle out that this guy was not so significant. But I'm just saying that for us, the 170921 or whatever the name is super significant. So that wiggle room you don't have. That's
so I imagine that you can discover a bunch of such events also in O3 data.
I hope that's what we are hoping when they give the data. One interesting thing about these events is that as you get heavier, you get more and more of the signal to noise just from the very end of the the merger. And at that time, the approximation that which is typically used for making the search, not for getting the parameters, but for making the search, the approximation that all of the radiation is coming from the quadrupole radiation is not true anymore. So one interesting thing to do that we are planning to do, and I don't know if we will be in time before somebody else does it, we are working on it, is to try to make the search for these heavy guys also, it's more complicated, but use templates that have also the addition of the higher octopole and so on radiation. And also to the extent that this might have any kind of in-plane spin they would process, and this makes it even more complicated. So there is some room that if it's true that there are all these heavier events, the searches might have a little also, in addition to the technical things about glitches and so on, maybe there's also some room that the templates that are being used are not the best ones. And so maybe there's a little bit of room for improvement, maybe one additional event from this.
Okay. Thank you.
Okay, thank you. I have a question. In the beginning, you said that all these events are surprisingly heavy, or at least most of the events that we started seeing. So, in which sense, surprisingly, is it due to the fact, can it be just observational bias, or we really didn't expect so many on astrophysical grounds?
I think the short answer is that before all the events that we had, all the black holes that we have, the stellar mass black hole came from these X-ray binaries that informed what we expect. Maybe, and the simplest explanation is all the black holes that there are out there are like the ones we see in the X-ray binaries. That's the 0th order. And you build them just like all the planetary systems look like ours before you see any other planetary system, right? So, so our models were built to fit the population of the black holes in the Milky Way and nearby. And that, you know, so the ones of LIGO were heavier than what you expect were to be producing, except maybe if you start tweaking the metallicity dependent and saying all these LIGO black holes are in some different environments, like early universe, and then I don't know. You have to do something. But most probably this is just that we were adjusting our things to the few things that we had seen in our galaxy. And somehow, I think it's also pointing that the things that you're seeing in X-rays come from a different channel or are seen, they're not all there is to it. And maybe there's some reason why the heavier ones are not seen in X-ray binaries. I don't know. Okay. I mean, there's time scales anyway.
Lance, you have your hand.
Yeah, if you don't mind, I'll ask another question. What do you think about the prospects of finding optical counterparts to the heavy black hole mergers? I kind of like this theory that they're in the accretion disks of supermassive black holes, and maybe there will be some optical counterparts as a result. What do you think?
Yes, I think, this was also proposed as a result of a particular example but this, I mean, in the end, I think was discredited, this flare or whatever. But okay. I think that's, or people, I think the chances that it was a real association was not particularly high. Could be by chance, I guess. But this is something that maybe could happen. Another avenue for this that is related to, so I said, that we had found, so let me backtrack. So these very, very far away events, in principle, there is some chance that they could be gravitationally lensed. This chance with all decent estimates is very small, but not negligible. So eventually, after you've seen hundreds of them, you will start seeing such things. I mean, somehow we managed to find something. I don't know. I have no explanation for it because there's, several of these images, several of these events are consistent with having the same parameters from the same location on the sky. Looks very unusual, but also lensing is very unusual. So I don't want to discuss our claim, but in the context of your question, once you detect a lensed case, if you can identify, the lensed galaxy and the lensed galaxy, then you will be able to you will be able to pin it down much better. So I think eventually that might be a way to have a population of black holes for which you will know the galaxy, because you will see the lensing effect of the galaxy in the optical, not the and the identification is not so it's pretty robust, because if you see multiple images, you have all the time delays of the gravitational waves. There's also, contrary to what just happens in optical lensing, there is a phase, you know, these images of in a gravitational lens, they have different parities, which for the optical usually doesn't matter. But in terms of the gravitational waves, this adds some phase shift of pi in some convention. Between, so all, you know, there's various pieces of things that need to fit together if you are really seeing a lens, and then if you have a proposed candidate lens system, you can check the location of the sky, the time delays, and so on. So I think there will be lensed events, you know, maybe not in 03, but a little bit later. And I think for those, you will be able to identify which galaxy it came from, and if there are some transients or something, now you have a individual galaxy, you may be able to go back and see if something was there. You know, they would be incontrovertible, I think.
So you're saying you can use the association with an optical lens to increase the chances of finding an optical counterpart?
Yes, because lenses are rare, right? Lenses, gravitational lenses in the optical are rare. So
thanks.
Yeah.
Thank you. Are there any other questions? Okay, if not, thank you, Matias, again for the nice discussion. And if you can give us the slides, we will publish them as well.
Great. I'll email them to you, or what?
Yeah, that's okay. Thank you.
Great.
And thank you very much, and have a good day.
Yeah,
and
great.
Thank you,
Thanks.
everybody.
Thanks for the invitation. Bye-bye.
Thank you, everybody, for the attendance.